purpose of this screencast is to demonstrate how to interpret heating curves and explain energy changes that occur during phase changes. We're going to start off by looking at a simulation together where solid ice starts off at negative 50 degrees and is heated all the way up to hot steam on a stove. So, if we watch the solid ice temperatures rising to 0 degrees and then it starts melting, notice how this is a flat portion of the curve. It stays at 0 degrees C the whole time there's a mix of ice and water until all the solid ice is melted. Then that liquid water, now that it's all liquid water at 0 degrees C, is heated up. Notice that every once in a while, a water molecule actually evaporates from the surface. So, when we think of temperature, it's a measure of average kinetic energy. And there's going to be a few particles that are going to have more kinetic energy than the average. They'll have enough to overcome all those intermolecular forces at the surface of the water and evaporate. And that's why a cup of water just left out at room temperature will slowly start to evaporate. Now we've heated the water up to 100 degrees Celsius and vaporization begins to occur. It starts to boil and it's going to stay again flatline at this phase change. The whole time that it's changing phases, it's going to be 100 degrees Celsius as the liquid water boils and becomes water gas. And it's not until all of the water has evaporated that the temperature of the steam can then begin to rise above 100 degrees Celsius. And then steam can continue to rise in temperature. So when you encounter steam, it's hard to know what temperature it is, and you can get a very severe burn from steam when you are unsure of what the temperature is. So be really careful around hot steam. Next, we are going to focus on the heating curve itself. This is a good place to pause the video and draw what you see on the screen right here. Make your heating curve really large to take up most of your page so that you have plenty of room to add a lot of details to your heating curve. Now that you have a heating curve, let's take a look at it. On the y-axis is temperature, so it's temperature versus the heat or the energy input on the x-axis. So we're going to look at how much energy is added over time and how that changes the substance, how it changes phase. So at step 1, we have all solid particles. They're tightly packed together. They vibrate, but they're not free to flow past each other. At step 2, we will have, so step 1 was solid. Step 2 will have a mix of solid and liquid. So at step 2, we're actually melting. And notice how we stay constant at 0 degrees. We're going to stay constant at the melting and freezing point of liquid water. Now, the melting and the freezing point are the same for any substance, but they're measured specifically for that substance. So since we're going to be working with water, we'll have 0 degrees for the melting and freezing point of water. So it's going to be melting at 0 degrees and it's going to stay at 0 degrees the whole time melting is occurring until all of the ice has melted. Then we'll be at step 3. At step 3, we'll have all liquid particles, and those particles are going to be farther apart. They're going to be free to move past each other. They're going to take on the shape of the container, but not its volume. And then at step 4, we'll have a mix of liquid and gas. And at step 4, this will be our vaporization step. Boiling that liquid to gas. So that at step 5, we have all gas. And these particles are going to be widely spread apart, free to flow past each other and taking on the shape of their container. So, to summarize, at step one, we have all solid. And what we're doing at step one there is we're heating up our ice. So we're heating up our ice from maybe -50 in our simulation. This looks like it might be -40 or so, all the way to 0 degrees C. So when we heat our ice, our temperature is increasing. And we know temperature is a measure of average kinetic energy. So the energy that's being added as we go up in temperature is kinetic energy. Then at step two, we have a mix of solid, ice, and liquid water. So we have this solid liquid mix. And what we are doing is we are melting the ice. So all the added energy goes into melting the ice. So temperature is constant. For water, constant at 0 degrees. Temperature is constant. Then where is all that added energy going? Well, to get from solid particles to particles spread much farther apart, or particles that are free to flow past each other, we're going to have to break some of their existing intermolecular forces. So that added energy is used to break the stickiness between the particles, the intermolecular forces. And so during that portion, where is all this energy going? Well, it's raising the potential energy of the particles. Potential energy increases when particles are farther and farther apart. Think about it this way. A ball that's laying on the ground has low potential energy compared to raising that ball up farther away from the earth. When you raise that ball up and you hold it up in the air, it's got more potential energy than when it's just laying on the ground. Laying on the ground, it's close to the earth. Holding it in your hands, you have brought those two particles farther apart and you've raised its potential energy. In step three, we have all liquid. Our added energy is being used to heat up that liquid water. So the temperature is increasing. The kinetic energy is increasing. At step four, we've got this liquid and gas mix as we vaporize or boil, if you will, that water. And when we're boiling that water, we're going to have to break all of the remaining intermolecular forces that have been holding it in the liquid phase. And so if you notice in that vaporization portion, that is a lot of energy added. It's a longer line on purpose because it's going to take more added energy to break all of those remaining intermolecular forces. So that boiling portion takes more energy than the melting portion of the phase diagram does. And we know that added energy goes to potential energy. Those molecules are farther apart, so they have more potential energy. And in the last step, we have all gas, and we are going to heat up that steam, heat up that gas. And as we do that, temperature increases and average kinetic energy increases. And that steam can get quite hot. We're unsure of the temperature, and so it can cause pretty severe burns. So what we can stop and look at is that as we move up the heating curve, we are adding in heat energy. And so our water absorbs heat energy, and that is all endothermic. Melting, boiling, or endothermic processes. This can be confusing because When students think of that water on that hot stove, for some reason, that hot stove makes us think exothermic, but it's that stove putting off heat. We have to think of our system, and here our system is the water. And what that system, what that water is doing is absorbing heat energy. And so that is an endothermic process. So let's just review a little bit. Step one is heating up the ice all the way to its melting point. Then at step two, we're going to be flat line during the phase change until all of the solid is liquid. And at that point, right here, all of the solid is now liquid. So now we are all liquid. Once we are all liquid, we can go ahead and continue heating to 100 degrees Celsius. At 100 degrees Celsius for water, we're going to go ahead and vaporize all of that water to steam until this point right here. And right there, we've got all gas. At that point, we're finally all steam. And now added energy is going to be used to raise the temperature of the steam. So these are just really alternating points on the heating curve. Alternating what is occurring. It's alternating between raising temperature, changing the phase, raising temperature, changing the phase, raising temperature. Now, let's think a little bit about a cooling curve. A cooling curve just heads in the opposite direction. You would remove heat energy. When you remove heat energy, that's actually exothermic because energy is going to leave the water and go to the surroundings. So even in freezing, for example, that's going to be exothermic. So we're going to change these steps, and instead of vaporization, we're going to have condensation. Instead of melting, we're going to have freezing. So if we think about these steps in reverse, we're thinking about cooling steam down to its boiling point, 100 degrees. Then we're thinking about steam condensing until all of the steam has condensed. Here we'd be all liquid. At this point, finally all liquid. Then we're talking about cooling the liquid down to its melting point, down to 0 degrees. Once all of the liquid is 0 degrees, then we can freeze the liquid. Once it's all frozen, then we'd have all solid at this point. We can start to cool the solid ice even below 0 degrees, below its freezing point. Now we're going to look at a cooling curve simulation. We're going to look at cooling steam at 150 degrees Celsius all the way to ice below its freezing point. So we'll show the steam cooling down to 100 degrees C, reaching that boiling point where it can condense. It's the same as its condensing point. And so it's going to condense until it's all liquid. And once it's all liquid, then it can start to cool below that boiling or condensing point down to 0 degrees C. Now, the whole time here, heat energy is leaving the system. And so since heat energy is leaving the system, it's exothermic. In order for those particles to slow down, they have to lose energy to the surroundings. And as they lose energy to the surroundings, they're going to make IMFs or make intermolecular forces that make the nice structure of this solid ice. So in order to make that nice crystalline structure, they're making new IMFs during the phase change portion. And now here again, this is exothermic. Energy is being lost to The surroundings. What might the surroundings be? Where is this exothermic energy going? Well, if this water was put in the freezer, that energy is going essentially to the coolant of the refrigerator or the freezer. And that is what is absorbing the heat energy that's being lost by the water. So, hopefully, now you know more about interpreting heating curves and can note the flatline portions of the heating curves where phase changes are occurring. For water, that's always going to be 0 degrees for melting or freezing, that flatline portion. There'll be a flatline portion at 100 degrees Celsius for boiling or for condensation. Then you'll have 3 points where temperature can change. The temperature of the solid can change. When it's all liquid, the temperature of the liquid can change. And when it's all gas, we can change the temperature of the gas. And then, of course, that steam can get very hot as you increase its temperature on a heating curve. So be really wary of hot steam and careful around it.